Good morning, good afternoon, and good evening, wherever you are in the world. We're going to get started with this keynote in just a minute here. Thank you for joining us. Okay, hello everyone. We'll get started now. Welcome, thank you for joining us. We're going to have a 1 hour long keynote session here, and it's going to be the speech followed by the Q&A. So if you have any questions, please type them into the Q&A section. And delegates, I request you to please keep your mics muted during the session. So I'm Harshmitha from the programming team, and I'll be moderating this session. It's my pleasure to present this keynote for SpaceGen United. I'd like to welcome our keynote speaker, Lindley Johnson. Thank you so much for joining us and taking the time out of your busy schedule to do this. And thank you to the NASA Planetary Defense Coordination Office. Lindley is currently assigned to NASA Headquarters Science Mission Directorate, Planetary Science Division, as the lead program executive for the Planetary Defense Coordination Office and the NASA Planetary Defense Officer, tasked with warning and response to any potential impact of Earth by an asteroid or comet. Prior to joining NASA in 2003, he served 23 years of Air Force active duty. He was the program executive for NASA's Deep Impact mission to Comet Tempel, and the lead program executive for the Discovery program of mid-class solar system exploration missions. There's also an asteroid named Johnson to recognize his efforts in detecting near-Earth objects. Lindley, the floor is now yours for the keynote, whenever you're ready.
Okay, thank you very much. I'm happy to be here and happy to be with you with some of my colleagues over the next 3 days for our Planetary Defense workshop with you. In the next 3 days, you're going to hear a lot of facts and figures and information about planetary defense. So today, I thought I'd take a little different take. You know, science, planetary defense is applied science, so to speak. We like to refer to it as applied planetary science. And so anything about science, though, it's not just, and the progression of science is just not facts and formula. There is also very much a human element as the knowledge and understanding progresses. So I wanted to talk to you about that a little bit today. So let me bring up some slides here, more for you having something besides having to look at my mug for the entire half hour or so here. So is that showing okay?
Yep, that's good.
Okay. So, you know, first of all, I want to say that this history of how did we get to planetary defense, I'm going to talk about 6 phases, areas of understanding that had to come into being before we really understood what the threat was out there from near-Earth asteroids and comets, and developed the ways and means by which we might be able to defend the planet should a hazard appear. But I also want to acknowledge that this is kind of, you know, from my perspective, being an American and educated up through a Western civilization perspective on things. So this is the story as I know it. I'm sure other countries and other cultures have their own story to tell, and I'd be delighted to learn about those other aspects. So let's begin. First phase of understanding planetary defense was the discovery of the asteroids, and it hasn't been all that long since we even knew that asteroids existed in the solar system. In fact, just a little over 200 years, when the first asteroid series in the main asteroid belt was discovered by just this gentleman. Of course, comets have been known for millennia because they occasionally become visible in the sky. And although the ancient Greeks thought that they were an atmospheric phenomenon, much closer to the surface of the Earth, it became known that they were solar system objects and went around in orbits around the sun just like the planets. Oh, sometime in the 1600s, with the knowledge of imparted by the discoverers of the planets and Sir Isaac Newton, and then was really put to bed by Sir Edmund Halley in his discovery of the orbit of Halley's comet, and being able to put together that previous apparitions of this comet had been seen and predicted its next approach visibility to the Earth in 1758, although he did not live to see that. But asteroids weren't known about until 1801, when Giuseppe Piazzi discovered what became known as Ceres. Now, that's not what they were hunting for at the time. They were hunting for the missing planet that had been predicted to be between Mars and Jupiter. And they had hypothesized that there should be a planet there based upon this regular progression of the planetary positions in orbit about the sun that was known as Boyd's law, although the actual developer of this understanding was Titius. And so Titius Bode's law is a understanding of a regular positioning of the planets in distance from the sun. Now, there's been some conjecture over the years about what's the physical meaning of this, and why did planets form in this somewhat regular progression. Sometimes it's simplified as the next planet will be about twice the distance from the sun as the previous planet, but it's not quite that simple. It was based upon the position of Saturn being about 100 units in distance from the sun. And on that kind of a scale, the position of Mercury was 4 units from the sun. Venus then at 7 units, 4 plus 3. And then the distance from Mercury to Venus times 2 is 6, and 6 plus 4 equals 10, which is the position of the Earth, which is 1 AU, and Saturn is at 10 AU. And so this worked fairly well and aided in the discovery of Uranus at almost exactly the right position at 20 AU. But then it kind of falls apart after that with Neptune and Pluto. But the position 28 in this progression, there should have been a planet there. And so a group of astronomers was formed in the late 1700s, early 1800s to search for this planet. And although Piazzi was supposed to be part of this celestial police, they called themselves, and aid in the search, apparently the message to him either didn't get sent or was delayed. But nonetheless, he was searching for the planet in that position when he came across Ceres on the 1st of January of 1801, a date, that starts the new era of the 1800s, 0101. So that's kind of interesting. But it was quickly realized that this body wasn't of the expected size, and there was a lot of controversy about what this new object was, because it obviously wasn't a planet like the others that had been known. And then it was the years that followed, it was understood that this was only one of many of these bodies that were in what's now called the main asteroid belt. And literally dozens were discovered over the next few decades as the capabilities of the telescopes and the technology used by astronomers progressed. And discovery of asteroids has since then progressed as the technology to find them did. And so the understanding of these additional small bodies in the solar system increased. And over the next, that century of the 1800s, some 450 of these asteroids were found, mostly in the main belt, though. Perhaps a few of them are what we now call Trojans. Hence the hunt for asteroids had commenced and had continued. The next phase of our understanding leading to planetary defense was an understanding of the impact effects. Now that there were these known objects out there, and in parallel, the understanding of the origin of meteorites, meteors weren't known to be caused by objects entering from space until about the same time frame as asteroids were discovered, although there had been conjecture prior to that. Earlier meteors and meteorites had thought to be rocks that had been ejected by volcanoes and with enough force to throw them many, many miles, and in fact, large distances from volcanic activity. But with the understanding now that there are other small bodies in space, and the observation of meteorite falls, it became known that objects do enter from space and perhaps could cause some damage, although there had not been well-documented occasions of that. But then in the second half of the 1800s, at least Western explorers found this large hole in the ground in eastern Arizona. Of course, we now know this today as Barringer Crater, or more commonly Meteor Crater. But it was originally seen by U.S. cavalry in 1873, although it had been known to the Native Americans for probably millennia before that, because there were iron meteorites, small iron meteorites found all around the site. Some of these meteorites have now been discovered as shrines in the archaeological remains of Native American villages in the Southwest. And this certainly was a source of respect by the Native Americans, and that gave them these this iron that could be formed into strong arrowheads and spearheads. Certainly an advantage over the flintstone arrowheads that the Native Americans in my part of the country where I grew up in Kansas had. So this crater was found, and a guy named Daniel Beringer came to this site. It was known as, actually for some inexplicable reason, known as Coon Mountain back in those days. And the origin, common understood origin of this formation was, again, volcanic. The conventional wisdom, so to speak, which sort of made sense because there are certainly a lot of volcanic cinder cones around that area of the Southwest. But this crater definitely had a different form than those volcanic caldera. And so it was thought that maybe this was a massive release of steam and heated gases caused by volcanic activity that blew back the surface and caused the overlap around the rim of surface material. But Daniel Beringer had the theory that this was a large meteorite that had caused this crater, a large iron meteorite based upon the remnants of the meteorites around the area. And so he thought that there's got to be a large iron mass at the bottom of that crater. And so he put in for the mining rights for this area and spent literally decades searching for that large iron mass at the bottom of this crater that he thought would make him rich. But that was not to be. He never found it. But the Beringer family, because of his establishment of these mining rights for this area, has owned this land to this day, and it's now a quite popular tourist attraction, one that I would highly recommend to anybody that hasn't been able to see it. If you're ever in Arizona on I-40 between Winslow and Flagstaff, it's only about 5 miles off the interstate there, and it's should be seen by anybody interested in this area. So the effects, the impact effects of a large object entering the Earth's atmosphere and colliding, the hypervelocity release of energy instantaneously. The only equivalent is the energies that are released by nuclear detonations of orders of megatons of TNT. And so Gene Shoemaker, who was a young geologist working for the U.S. Geological Service in the 1950s, based his foundational report on the origin of Beringer crater on the impact of an iron meteorite, and conclusively proved that this was the cause of it. Gene Shoemaker was also involved in the space exploration program and the Apollo moon project. He instructed the astronauts on their geology of the moon and how to pick out good samples to return. Craters on the moon, there had been controversy about their origin too, as much as up until the 1950s. The origin was thought to perhaps be volcanic, but the return of the Apollo moon samples conclusively proved that that they were caused by impacts due to the shocked wrecker that was returned with those samples. So the next phase on planetary defense is discovery of the near-Earth object population. And again, June Shoemaker and his wife Carolyn were very much involved in this. After the Apollo program, Gene went about investigating further what the hazard was from asteroids impacting the Earth. Now, the first near-Earth asteroid, 433 Eros, was found about 100 years after the first asteroid in 1898. 1898 DQ is Eros' original designation, and its number 433 means it was one of the 433 named numbered asteroid. At that time, with only one near-Earth asteroid known, there were already 27 near-Earth comets that were already known. By the mid part of the century, 1950, there weren't very many additional near-Earth asteroids known. There was only a dozen, 12, by 1950, whereas near-Earth comets had almost doubled to 40. Even 20 years later, in 1970, there were only 27 known near-Earth asteroids, and about double that number of near-Earth comets at 47. It wasn't until the 1980s and early 1990s that the discovery of near-Earth asteroids really took off, and it's due to these four individuals really on this slide. First of all, Gene and Carolyn Shoemaker, as I said. After the Apollo program, he went about trying to determine what the hazard really was to Earth of asteroid impacts, and he and Carolyn became asteroid hunters, taking photographs of the sky on a regular cadence, and then comparing those photographs one to the other to discover a movement of an object across those images. Another prominent asteroid hunter at the time was Eleanor Helene, there in the middle at the bottom, working for JPL. She actually teamed up with the Shoemakers for a while in their project, and then started her own near-Earth asteroid tracker project at JPL. And Tom Garrels on the right at the University of Arizona. And it was Tom Garrels who actually gave me my start in this business. While I was still in the Air Force, I was stationed at Albuquerque, New Mexico at the time. And he came to talk to us about space surveillance capabilities and the advent of charge coupled devices, charge coupled CCD imagers. I wanted to work with us on development of that technology. And he told me what he was all about in finding these near-Earth asteroids that could be an impact hazard to the Earth. And I thought that was something that of great interest and importance, actually, as our understanding of what the hazard and threat might be there that required a more national effort to determine what the real threat was. So these individuals as asteroid hunters in the U.S. Were all certainly inspirations to me and to the current generation of asteroid scientists and the planetary defense community. And if we can pass on to you, the next generation, the same inspirations of any near the level that they inspired us, we will have done our job. So By the start of NASA's NEO program in 1998, 500 near-Earth asteroids had been discovered, a little over 500, and it's due to the efforts of these individuals prior to a more well-supported program being started at NASA. And now today, there are some 23,100 near-Earth asteroids of all sizes known, and 110 comets. So in parallel, about this same time frame, there was also the realization of the continued threat from the asteroid impact. And part of this comes from the work of the Alvarez team, father-son team. The geologist Walter Alvarez had found in his geological surveys around the world this layer of iridium in many locations of enriched iridium, and trying to find an explanation for this. Why was this layer of enriched uranium so pervasive around the Earth's surface? Well, together with his father, Louis Alvarez, a physicist, they developed the theory that it was caused by a impact of a large asteroid or comet somewhere on the Earth's surface that had caused the ejecta of this cosmic material, the enriched iridium, not common on Earth, but common in meteorites. An impact, and it coincided at the same layers as the demise of the dinosaurs, and so the theory then was that this had led to the extinction of the dinosaurs and some 75% of the other species on the Earth's surface at that same time in the geological record about 66 million years ago. So there's this nice drawing here of the Tyrannosaurus Rex fleeing in panic from the ejecta from a large impact. So that was in the 80s. Then also with the work that was being done by the Shoemakers, now with David Levy, the discovery of Comet Shoemaker-Levy 9. By Carolyn Shoemaker, and some of the images that had been taken back in 1993. And the reporting of this squished comet, as she originally described it, but then it was seen as a string of pearls of comets orbiting Jupiter. And as reported to the Minor Planet Center, and then predictions of the orbit of that those comet fragments made by individuals like Don Yeomans and Paul Chodas out at the Jet Propulsion Laboratory in an area that was known, now known as the Center for NEO Studies, predicted the impact of Comet Shoemaker-Levy 9 on Jupiter in July. Through several days in July of 1994. And a lot of astronomers working in this area today, got their start with the impact of Shoemaker-Levy 9. So that just, proved that celestial impacts weren't something of bygone billions of years ago. They still occurred in the modern day solar system, and we're still a threat of planetary impact. So what do we do about it? This led to the start certainly by NASA per direction of U.S. Congress for a search program for at least the larger near-Earth asteroids and comets, what became known as the NearEarth Object Observations Program, started in '98. We were tasked to find the 1 kilometer and larger objects, and then as the understanding of how much damage could be done by even smaller objects came to light, our threshold was then in 2005 reduced down to 140 meters and larger. But the thought of how do you deflect an asteroid that's on an impact trajectory to the Earth, studies of that go back further than you might think. The close approach of Earth by the asteroid Icarus back in 1967 actually prompted a study by MIT students in systems engineering project that became known as Project Icarus, where they found that the only source of energy large enough to possibly deflect an asteroid of that size would be a nuclear bomb, nuclear weapon, actually a series of them launched on a Saturn V would be the only way to protect the Earth. Of course, that kind of action and thinking, prompts a lot of perhaps negative reaction in having to do it that way. And so, a search for a better way of responding to these actions, this threat. This understanding gained in the '90s also prompted the United Nations and the Committee on Peaceful Uses of Outer Space out of the United Nations Unispace 3 conference to add the subject of NEOs and appropriate international actions to respond to a possible impact threat to their program of activities. It was one of many. In fact, it was the 14th on their list of activities that undertake over the next 10 to 20 years. So Action Team 14 was established by the United Nations Committee on Peaceful Uses of Outer Space. It really didn't get started in its activities until about 2007, after a number of the quote-unquote higher priority issues had been undertaken, and then that formed the NearEarth Object Working Group, who was ready to make recommendations to the Committee on Peaceful Uses of Outer Space on a date that became of greater significance. We were developing our report, and we're going to brief it out on the floor of the Scientific and Technical Subcommittee on February 15th of 2013. That turned out to be another landmark day in planetary defense, with the entry of the 20-meter object over Chelyabinsk, Russia. That we all awoke to news of that morning, and it was suddenly a very hot topic for the committee, and they had then passed our recommendations of forming these groups, the International Asteroid Warning Network and the Space Mission Planning and Advisory Group, which we're going to hear more about tomorrow. Those activities passed through the subcommittee and the committee and on to the General Assembly without much discussion about the need for these kind of capabilities. So finally, and that gets us now to the modern today, where we are with planetary defense, that we will be talking to you about here over the next a couple of days, and then working with you on the workshop. So with all of that, I've exceeded my time here now, I see, as far as talking, but I wanted to leave you with a couple of thoughts. Not only in science, but in other pursuits in life, that first of all, you may not find what you're looking for. In fact, what you may find is something much more marvelous. The astronomers were looking for the planets, and they found the asteroids, and led to our understanding of what asteroids are, better understanding of the formation of the solar system, and also to our understanding of a continued threat, albeit rare, but of high consequence of the asteroid impact. So keep an open mind of what you look for in life and want out of life. The other thing is beware of conventional wisdom. In several cases, the conventional wisdom was this can't be a impact from space. Objects, small objects, can't be out there, and even if they are, they will never impact. But you should always be objective. Look at the facts, find out the facts for yourself, and all the facts, not just those that support a particular theory or understanding, but what's all the facts. Often, all of these facts will be conflicting, and only you can decide what's really the right course for yourself. So with that, I only want to make one other thing to say here, and that is that if you want to have further reading about what all I talked about, I want to recommend a book to you. It's let's see, it looks like my video is frozen. Is that right?
It's actually not turned on.
Okay, let me try it again here. Oh, there we go. Well, still not moving, eh?
No, not yet.
Well, I want to recommend a book to you. I was going to show it to you, but okay. I'm trying to start my video. My camera shows it's on, but it doesn't show any motion. Maybe my link is not supporting things here right at the moment. Here, let me try something. Okay, I'm back. You hear me now?
Yes, we can hear and see you.
Okay, here's the book, Fire in the Sky by Gordon Dillow. Tells a lot of the elements of the history, the human history that I've talked to you about. It's a very well-researched book, and I recommend it to whatever your background is, be it science or any other area of endeavor. It's a very readable story by everyone. And I even play a short cameo role in the end. So, okay, with that, sorry I went over, but I'm happy to take your questions.
All right, great. Thank you. Thank you so much for that presentation and for shedding some light on the history of planetary defense. So we have a few questions here. I guess the first question, it's a big one that a lot of people will have, is Pranjal from India is asking, what are the emergency protocols in place if we notice a near-Earth object coming towards the Earth with a potential collision course right now?
Well, you're going to see some of that in the presentations in the next day or so. First of all, finding it and establishing what the orbit really is. Often with the first observations that come in, the possibility of an impact might be uncovered, but the uncertainties may still be large. And so we really have to collect more observations and understanding of what the orbit is to determine whether it's really an impactor or just going to be a near miss. And then, working within the International Asteroid Warning Network to get a common understanding of what the threat level really is. Is this going to impact? How big is the object? What might be the effects if it were to impact wherever it might be predicted to impact. And then working with our international colleagues at other space capabilities, it's not going to be one space agency, one nation that undertakes a single mission to go deflect the asteroid. This has to be a campaign of several missions that involve space agencies of several nations. And so all that has to be planned and coordinated, and that's what the activities that we're going to talk about on IWAN and the Space Mission Planning and Advisory Group, same page, are all about.
Okay, and so for now, there's so many near-Earth objects that have been detected and classified. So is there a way to statistically or mathematically evaluate their trajectories and to be prepared and in future emergencies?
Well, certainly statistically, you can predict the frequency of which impacts might occur, but that is, are just probabilities. It is a random process, and therefore, although statistics might say, a major impact only occurs every 1,000 years, it also could occur next week. And so even though statistics might show you, the level of the hazard, they won't, find the specific threat that needs to be dealt with. And so although that is an element of the study, we still have to be looking for them and to find to find when is the next major impact.
Okay, so we have another question here about, is there a possibility to send a rover on near-Earth objects to get some more data, or could this pose any dangers by changing the path, or how would that work?
Well, it depends on the asteroid and what orbit it's in. I wouldn't want to do that on, say, Apophis, who's predicted to have a very close approach to the Earth in April of 2029. That's kind of a situation where, don't touch, at least until after this close approach. But certainly other near-Earth asteroids, there's a variety of different compositions. We need to understand all those compositions to have a better understanding of how deflection effects might be done. And I wouldn't probably a rover because of such the low gravity that is on these bodies. A rover wouldn't work too well, but certainly a hopper, something that hops around from one place to another on the surface might be a practical application.
And on that note, could you tell us a little bit more about some of the future missions that are planned?
Well, again, you're going to hear about those the next couple of days. You will hear about the R double asteroid redirection test mission, which is in spacecraft is right now in integration and test phase. scheduled for launch exactly a year from now, on the 22nd of July 2021, to impact the moon of the Didymos system, now called Dimorphos, in October, well, late September, early October of 2022, to test a kinetic impact technique for deflecting an asteroid. Right now, we have the OSIRIS-REx mission, NASA's OSIRIS-REx mission. It's about to collect a sample from the near-Earth asteroid Bennu, collect that sample and bring it back to Earth in 2023. But the Japanese have already collected a sample from an asteroid, Ryugu, with their Hayabusa 2 mission, and it's on its way back to Earth now.
Okay, and you mentioned that you're working also on an international scale. So what are the efforts that are being made to support each other in the event of a potential collision?
Well, that's what the Space Mission Planning and Advisory Group, what we call the same page, is all about, is to get all of the national space agencies on the same page on what technologies and techniques might be appropriate for different situations that we might be faced with. So we have a common understanding of what can be effective and how we can work together to deflect a potential impact threat.
Okay, so in a case that a collision course cannot be prevented, how does PDCO prepare the people near or at the impact zone, or is that a part of your work?
It's not directly a part of our work, but it is work we support. First of all, with the observations and orbit prediction, getting as precise an orbit as we can, so we know when the time and therefore the location of the impact is, so we can alert the emergency response authorities to that, and characterization of the asteroid. How big is it? What's its composition? So we get a understanding of what the effects might be. How bad will the impact be? Is it object small enough, so loosely packed that the Earth's atmosphere is pretty much going to take care of it, or is it a larger object, very coherent object that could make it all the way to the ground and cause an impact crater like Beringer crater that I showed you earlier? If that were to occur in the modern day, pretty much all of eastern Arizona would be wiped out by the air blast from it. And so that's the kind of information and assessment that PDCO and our partners and other agencies, including other U.S. government agencies, need to pull together to advise the emergency response community of what they may be facing. But the emergency response community, civil defense, however you characterize it in whatever country, has a lead if we have to take the hit on the ground.
Okay, and so what about for geostationary satellites? Does PDCO also keep an eye on satellites and defense against them?
Well, again, not our responsibility to do those predictions. Our responsibility is to advise those agencies, which in the U.S. is the Air Force, well, now U.S. Space Force, and for national security assets, and Goddard for civil assets. We tell them what the orbit is, and then they are able to compare that to the satellite orbits to determine if there is a potential collision hazard. Extremely rare event, but not out of the realm of possibility.
And also kind of related to your scope, do you also track collisions with other celestial bodies like the Moon or Mars?
Well, actually, we do. The Center for NEO Studies looks at impact predictions, not only the Earth, but all the other celestial bodies, planets as well. Here, 3 or 4 years back, we're tracking an asteroid that not only crossed Earth's orbit, it crossed Mars' orbit as well. And it looked like it was going to be, pretty close, maybe even an impact. But as additional observations came in, we eliminated that possibility.
And so overall, we have all these organizations working internationally within like NASA PDCO. What can be done on a smaller scale in this field?
Well, certainly any institution, country with smaller, what I call meter class telescopes, and what I mean is anything from 0.5 meter size aperture, up to 1.5 or so, can join with the observations of the asteroids. As I was talking about, in establishing and get a higher precision orbit, we have to get observations over time of this object. So those observations come in from observatories around the world, some of them amateurs, some of them amateurs with somewhat sophisticated equipment, provide observations to the Minor Planet Center, where they are all collected and used to determine better orbits for all the known near-Earth asteroids. So that's certainly an area that a lot of people can get involved. There's also some citizen science projects. The International Asteroid Search collaboration, ISAC, actually has a program to train students how to find asteroids in images that are provided by the professional survey observatories. Sometimes our automated processing of the images doesn't always collect all the asteroids that are in those images. And so they go through all the images and find more objects, largely main belt or Trojan asteroids. But that's another area that almost anybody could get involved with.
Okay, great. I think we have time for one more question. So how does the Planetary Defense Coordination Office interact with Congress to enable policymakers to understand the need to support research in this field and allocate funding to continue your work?
Okay, well, that's not only a challenging question, but it's a challenging issue, and something that Planetary Defense Coordination Office also works. As we submit our proposed budget every year through NASA up through the White House for approval for getting it into the president's budget request that then goes over to Congress. We provide what our current understanding of what the hazard is, our progress toward finding all these objects, and what is it that we need to improve and enhance our capabilities for the future, and that budget justification. So that's sort of how that process works. We also get requests on a frequent basis from congressional staffers to inform them, bring them up to speed on what the current state is.
Okay, well, I think that's all the time we have today. Thank you again so much for joining us here.